Alright, let's go. Number 10. The paradox Einstein built to kill quantum mechanics. In the spring of 1935, Albert Einstein was not trying to discover anything new. He was trying to finish off a theory he despised. Working at the Institute for Advanced Study in Princeton with two younger physicists, Boris Podolsky and Nathan Rosen, Einstein wanted to prove once and for all that quantum mechanics was an unfinished sketch of reality, not the final picture. Standard physics at the time said a particle's properties don't exist in a definite state until measured, and that measuring one particle should have zero effect on a different particle far away. That's just locality. That's just how cause and effect are supposed to work. Einstein, Podolsky, and Rosen constructed a thought experiment involving two particles created together and then separated, and showed that quantum theory predicted something impossible under those rules. Measure one particle here, and the other particle's properties become instantly fixed, no matter how far away it is. Einstein, Podolsky, and Rosen published their argument in Physical Review, Volume 47, pages 777 through 780, in May of 1935, under the title, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" Their answer was no. Physicists tried to explain it away. Maybe the particles secretly agreed on their properties in advance, like two coins flipped at the same casino using the same rigged dice. Maybe there was a hidden variable nobody had found yet. Every attempt hit the same wall. Quantum mechanics kept making the correct predictions anyway. Einstein died in 1955, still convinced the universe could not be built this way. He was building the case against something that would later be proven correct. And correct in a way he called spooky. If Einstein was wrong about locality itself, then two particles on opposite sides of the room you're sitting in right now may be linked in a way no signal, no force, and no distance can explain. What exactly is passing between them, and how fast is it actually happening? Bell didn't stumble onto the answer. He went looking for a way to end the argument for good. Number 9. The theorem that closed the escape hatch. In 1964, physicist John Stuart Bell was working at CERN, mostly on particle accelerator theory, treating the Einstein-Podolsky-Rosen debate as a side project nobody had properly settled with mathematics. For 30 years, physicists on both sides had argued in prose. Bell wanted numbers. Standard interpretation held that if hidden variables existed, quantum predictions and hidden variable predictions would eventually diverge in a testable, measurable way, but nobody had built the actual test. Bell derived a mathematical inequality that any theory based on local hidden variables must obey. No exceptions. Then he showed that quantum mechanics predicts results that violate that inequality outright. Bell published the result in the journal Physics, Volume 1, pages 195 through 200, in 1964, under the modest title On the Einstein-Podolsky-Rosen Paradox. The paper sat almost unread for years. Physicists proposed that measurement devices themselves might secretly communicate, or that the universe was somehow rigged from the start to fake the violation, a position called superdeterminism. Neither explanation could be tested, disproven, or taken seriously by working physicists, so both were quietly abandoned as untestable rather than solved. What Bell had actually done was corner the universe into a choice. Either objects have real properties before you look at them, or nothing is truly separate from anything else once it's touched something else. Every particle inside your own body, once touched, collided with or exchanged energy with other particles going back to the Big Bang. Bell's math says separateness itself might be the illusion. Which one of those two options would you even prefer to be true? Nobody wanted to test it for real. Then somebody finally did, and kept closing every door. Number 8. The confirmation nobody could argue with anymore. By the early 1970s, physicist John Clauser at Berkeley wasn't trying to overturn physics. He was trying to build lab equipment good enough to actually run Bell's test, something theorists had left undone for a decade. Bell's inequality predicted a specific numerical boundary that any local, realistic universe could never cross. Standard physics said that boundary was safe. Clauser and graduate student Stuart Friedman ran calcium atoms through polarizing filters in 1972 and watched the boundary get violated. Physicist Alain Aspect at the Université Paris-Sud refined the experiment in the early 1980s, switching detector settings after the particles had already left their source, closing a loophole that let skeptics claim the detectors were somehow rigged in advance. Physicist Anton Zeilinger at the University of Innsbruck closed a further loophole in 1998. Then in 2015, 3 independent teams, including Ronald Hansen's group at Delft University of Technology using electron spins separated by 1.3 kilometers, published results in Nature and Physical Review letters closing every remaining loophole simultaneously. Skeptics proposed the detection loophole, the locality loophole, and superdeterminism. One by one the experiments closed each door. In October 2022, Aspect, Clauser, and Zeilinger shared the Nobel Prize in Physics for this exact body of work. Local realism, the comfortable idea that objects have fixed properties and nothing outruns a signal, is no longer a live hypothesis among working physicists. It lost, on camera repeatedly, for 50 years. Every atom in your hand right now is obeying a rule that forbids the universe from being built the way it feels like it's built. What does it mean that reality keeps failing the test we designed to save it? If it works in a lab across a table, the next question is obvious. How far can it actually reach? Number 7. The satellite that broke the distance record. In 2016, physicist Jian Wei-Pan and his team at the University of Science and Technology of China weren't trying to prove anything new about entanglement itself. They were trying to solve an engineering problem. Entangled photons degrade rapidly over distance through fiber optic cable. So ground-based experiments had capped out around 300 kilometers. Standard expectations said pushing entangled photons through Earth's atmosphere over 1,000 kilometers would introduce so much noise and photon loss that the entanglement would simply not survive the trip. Using the Messias satellite, launched in August 2016. Pan's team beamed entangled photon pairs down to 2 ground stations in the mountains of Tibet, Dalinga and Lijiang, separated by 1,203 kilometers, and the correlation held. Pan's team published the results in Science, volume 356, pages 1140 through 1144, in June 2017, reporting a Bell inequality violation of 2.37, plus or minus 0.09, more than 10 times the previous distance record achieved on the ground. Engineers had worried atmospheric turbulence, sunlight interference, and satellite tracking error would each independently destroy the signal. None of them did. Pan himself compared the achieved precision to detecting a single struck match from the surface of the moon. If entanglement survives over 1,200 kilometers of open sky without a single wire connecting the 2 ends, there may be no upper limit to the distance at all. Somewhere above your head right now, in principle, a particle could be linked to something on the far side of the planet. How far does the correlation actually stop, if it stops at all? Confirming the link was step 1. The next team wanted to know if you could send something through it. Number 6. The night they moved a quantum state across a room. In 1997, physicist Anton Zeilinger's team in Innsbruck, Austria, was working on a purely theoretical proposal published 4 years earlier by IM researcher Charles Bennett and colleagues, an idea for transmitting quantum information without physically moving the particle carrying it. Standard physics held that you cannot simply copy an unknown quantum state. Measuring it collapses it, destroying the very information you were trying to read. That's the no-cloning theorem, and it looked like a dead end for transmission. Zeilinger's team, led by Dick Baumeister, found a workaround using entanglement as the delivery mechanism instead of direct measurement. They fired an ultraviolet laser through a crystal to generate entangled photon pairs, then performed a joint measurement between an unknown photon and one member of an entangled pair, and the distant partner photon instantly took on the original photon's exact polarization state. Baumeister, Pan, Madel, Eibel, Weinfurter, and Zeilinger published the result in Nature, volume 390, pages 575 through 579, in December 1997, reporting an average fidelity of 0. 81. Comfortably above the two-thirds threshold required to prove it wasn't a statistical fluke. Skeptics proposed the result might be an artifact of imperfect photon detection or leftover classical correlation from the crystal source. Both were ruled out through repeated trials across multiple polarization angles. Nothing physical crossed the gap between the photons. The information did. No particle of matter moved. And yet the state itself, the actual identity of that photon, reconstructed itself somewhere else entirely. If information can relocate without ever crossing the space in between, what does location even mean for anything built out of quantum particles, including, at the smallest scale, Teleportation needed 2 photons that had already met. The next experiment removed even that requirement. Number 5. The entanglement between particles that never touched. In 1993, physicists Marek Yukowski, Anton Zeilinger, Michael Horn, and Artur Eckert were working through a purely mathematical problem about how to build long-distance quantum networks, since entangled particles degrade the farther they travel, and repeaters were needed. Standard intuition said entanglement could only exist between particles that were created together, or had directly interacted at some point, sharing a common origin. Yukowski, Zeilinger, Horn, and Eckert proved mathematically that 2 particles with 0 shared history could become entangled with each other anyway, through an intermediary measurement performed on a different pair entirely. They published the proposal in Physical Review Letters, volume 71, pages 4287 through 4290 in 1993, calling the process entanglement swapping. Laboratories worldwide spent the following decade confirming it experimentally, generating 2 separate entangled pairs, sending 1 photon from each pair to a middle station, and performing a joint measurement there, which instantly entangled the 2 outer photons that had never occupied the same space or interacted in any conventional sense. Early critics proposed the outer photons must be exchanging some kind of hidden signal through the source apparatus. Tighter timing controls and later experiments closed that possibility by separating the measurement events beyond light-speed communication range. 2 particles born in completely different places, with completely different histories, sharing nothing physical, end up bound together by a measurement performed on entirely different particles somewhere else. Entanglement, it turns out, isn't a relationship between 2 things. It's something that can be manufactured out of nothing shared at all. If connection doesn't require contact or origin or history, what other quiet threads might already be running between things you assume are unrelated? That was strange enough. Then Zeilinger's team asked what happens if you delay the choice until after it's supposedly too late. Number 4. The experiment that reached back in time. In 2000, physicist Asher Perez proposed a genuinely uncomfortable thought experiment. What if you could decide whether 2 photons had been entangled after they'd already been measured and detected, possibly after they no longer even existed as photons at all? Standard cause and effect said this should be nonsense, since a choice made in the present cannot alter a measurement outcome already recorded in the past. In 2012, Xiaosong Ma, Zeilinger, and colleagues at the University of Vienna built Paris's Gedanken experiment into real hardware. They generated 2 separate entangled photon pairs, measured 2 of the 4 photons immediately, and used a quantum random number generator to delay the measurement choice on the remaining 2 photons into the future, after the first 2 had already been recorded and locked in. Ma, Zotter, Koeffler, Ursin, Genuine, Bruckner, and Zeilinger published the results in Nature Physics, Volume 8, pages 479 through 484, in 2012. Whether the 2 already measured, already finished photons showed up as entangled or as ordinary and unconnected depended entirely on a choice made afterward. Physicists proposed this was merely a statistical artifact of selecting data after the fact, a form of retroactive cherry-picking. The debate over that objection continues in the literature to this day without full resolution. What can be said without dispute is that the correlation in the earlier data matched the later choice with total consistency, every single time. Nothing was sent backward through time in any way you could use to change an outcome. but the pattern and results already written down behaved as though the future had a vote. If the order of cause and effect can bend even this slightly under laboratory conditions, how confident should you be that your own memory of this morning is as fixed as it feels? None of this answers the oldest question in the room: what actually counts as a measurement in the first place? Number 3. The problem nobody has solved in a century. In 1932, mathematician John von Neumann wasn't trying to create a philosophical crisis. He was trying to give quantum mechanics a rigorous mathematical foundation, something the field badly needed after a decade of improvised rules. Standard quantum theory said particles exist in a spread of possible states, described by a wave function, until a measurement forces one specific outcome. Simple enough, until von Neumann asked the obvious follow-up question in his own formal treatment: what physical process actually counts as a measurement? A human eye? A photon detector? The air molecules that bump into a device milliseconds before a human ever looks at the readout? Von Neumann's formalism showed the collapse could, in principle, be pushed anywhere along that chain, with no privileged stopping point built into the mathematics itself. Physicist Eugene Wigner sharpened the problem in 1961 with a scenario now called Wigner's friend. An experimenter measures a particle inside a sealed lab, collapsing its state, while a second observer outside the lab, lacking that information, must describe the entire lab, colleague included, as still existing in an unresolved superposition. Both descriptions are mathematically valid. Both cannot be simultaneously true about the same room. Physicists proposed the collapse happens at consciousness itself, at any irreversible physical record, or that it never happens at all and every outcome simply keeps branching. None of the three positions has ever produced a way to be experimentally distinguished from the others. There is no settled answer, only competing interpretations that have survived, unresolved, for over 90 years. Every time you check your phone, glance at a clock, or simply decide to look up, you are performing an act physics cannot define. What precisely are you doing when you observe something? Maybe the answer is that nothing collapses at all. Maybe it just hides from you, extremely fast. Number 2. The reason you've never seen it happen. In 1970, physicist H. Dieter Zeh at the University of Heidelberg was trying to patch a gap in the mathematics of measurement, not overturn anything about daily experience. Standard quantum theory technically allows large objects, entire rooms, entire people, to exist in quantum superposition, spread across multiple states at once, yet nobody had ever observed a chair, a cat, or a person doing this. Zeh showed that the Schrödinger equation itself explains the silence. Any quantum system constantly interacting with its environment, air molecules, stray photons, thermal radiation, gets its delicate superposition destroyed almost instantly, smeared out into what looks like ordinary classical randomness. Physicist Wojciech Zurek at Los Alamos National Laboratory extended the idea through the 1980s and 1990s, publishing the formal pointer basis framework in Physical Review D in 1981 and a comprehensive review in Reviews of Modern Physics in 2003, terming the process inselection, environment-induced superselection. Zurek's calculations showed that for a macroscopic object like a dust grain, superposition survives roughly 100 millionth of a second before the environment forces it into a single definite state. Physicists initially proposed decoherence alone might fully solve the measurement problem outlined a paragraph ago. Zurek and others eventually acknowledged it explains why we never see superpositions, but not why any single specific outcome gets selected over the others, leaving the deeper question technically unresolved. So the quantum weirdness never actually disappears. It happens constantly, inside you, right now, in every atom of every cell. It just gets erased from view faster than any nervous system, including yours, could ever register it happening. If reality is quietly running on, rules this strange every fraction of a second inside your own body. How much of what you call solid is really just too fast to catch? 10 discoveries. One thread running under all of them. Number 1. The fact that was never actually explained. Two particles, Entangled once, remain correlated no matter how far apart they later travel, a link that has survived every experiment designed specifically to break it, for over 90 years, without a single physicist ever explaining what the connection physically is. Not what it does. Not how reliably it does it. What it is. Einstein tried to prove it couldn't be real, and lost. Bell built the exact test that could have vindicated Einstein, and it didn't. Clauser, Aspect, and Zeilinger spent 5 decades closing every possible escape hatch, one at a time, and won a Nobel Prize for confirming something nobody can fully explain. Teams have swapped entanglement between particles with no shared history, teleported quantum states across a room, and produced correlations that appear to answer to choices made after the fact. At no point in 90 years has anyone published a mechanism, only better and better confirmations that the mechanism, whatever it is, keeps working exactly as predicted. This is not a gap at the edge of physics, a rounding error in some obscure calculation nobody relies on. Entanglement sits underneath quantum computing, quantum cryptography, and the basic mathematics every physicist uses every day, fully trusted, fully unexplained. The universe is not confused about how it works. We are. Every anomaly on this list wasn't found at the fringes of a shaky theory. It was found sitting quietly at the center of the most rigorously tested framework human beings have ever built. If the best confirmed link in all of physics still has no answer for what it fundamentally is, maybe the question was never, does entanglement work? Maybe it was always what else is connected right now, in ways we haven't built an experiment sharp enough to catch yet. If you want to see more videos like this, click the video on screen now.